ceramic fabrication and processing. I guess most of you will be taking it as an elective, and I do assume that you have some background on ceramics technology, the basics of it. This course will take you through fabrication of conventional ceramics to the most modern ceramics, which can be fibers, coatings, and all of that. Today, I shall talk of what are the learning objectives, what shall we cover in this course, so that our goals, expectations are very clear. Ceramic, the journey of ceramics started more than 125,000 years ago. The first fires, which were accidental fires, that happened around 400,000 years ago. But it was only around 125,000 years ago do we have the idea that man could use fire under controlled conditions. That is, they could light the fire, have some hearth, that is, some covering so that the fire does not die out, and as a result they kept on burning the wood at the same place over and over again. The ashes collected, and slowly those ashes converted by reacting with the soil to the earliest form of ceramics. In fact, it was at the Clysis River mouth cave in South Africa over 125,000 years ago do we have the first evidence of controlled fire or hearth fire being made. What are ceramics? From 125,000 years ago, the definition of what are ceramics today has extended hugely, and it is impossible to define what are ceramics in very simple terms. However, one definition that comes out very clearly, that it is burnt stuff. This word is a Greek word, and all ceramics are processed by burning. As you will see through the course, we can have ceramics generated at temperatures as low as 130, 140 degrees centigrade, which are ceramic coatings on polymers, to ceramics which are for service at temperatures as high as 2100 degrees centigrade. Ceramics, as you know, can be both crystalline or non-crystalline. And I hope you are aware of the terms what are crystalline and non-crystalline. All of you buy figurines, that is, small figures which you go to various places and buy them. The first figurine was found at Dolio Venstanis in Czech Republic, where this was the first example where a man-made object was shaped and then burnt in fire to give a very dense sintered body. This goddess figure was made from burnt soil. For those of you who are interested, I have given you the URL link. Intellectual property rights issues prohibits me from showing you the picture. You can look up the URL link and explore what happened 26,000 years ago. This is where from the real ceramic fabrication and processing started. You should notice that most of the ceramics in early days were made from the soil beside the great rivers. It was Yangtze in China, the Sindh Valley in India, Tigris, Euphrates in Middle East. The reason simply is this: these rivers have a lot of kaolin. I will deal with kaolin and other aspects later. This kaolin helped in fabrication of ceramics. And it is amazing that our ancestors, who did not have any of the modern tools, were observant enough to decide what type of soil to use for making these figures without any temperature control which we employ today, without the controlled atmosphere we employ today, and yet get them. If I look at the timeline of ceramics, as I said, it started off 24,000–25,000 years ago, where the first ceramic figurines were made. The first fired tiles were made in India and Mesopotamia over 14,000 years ago. The real pottery making began in around 9000 BC in Egypt. This is where ceramics took a quantum jump. The Egyptians discovered glazes. Glazes are the shiny stuff that you see on your dinnerware, on your cups and vessels. This was a real quantum jump. And around 1500 BC, the Egyptians found out how to make glass vases. It was a glass drinking cup, glass materials. As an aside, I would like to say that today a lot of you talk of nanotechnology. There is a glass cup at Louvre Museum in Paris, manufactured in 1500 BC in Egypt, which has nano gold in it. I would only say that there are a lot of jargons we use like nano and all of that. I would like to emphasize it is nothing new. The reason why I say this is whatever the humans learned starting 25,000 years ago to 1500 BC was employed in making the newest ceramics, synthetic ceramics, which were essential for industrial revolution. Industrial revolution demanded that we learn how to melt metals. We learn how to forge metals. It required much higher temperatures, very high controlled atmospheres. And the knowledge gleaned from 25,000 BC to 1550 AD is what we are still relying upon while fabricating ceramics today. It is true that with modern tools we understand ceramics more. What is it? How to control things, how to make engineer materials. But I would like to emphasize that materials we are discovering today are merely re-engineered products which were discovered even before Christ was born. Why do I say this? I am showing on the screen two dinnerwares. The one of your left is a China dinnerware, and the one on your right is Vitrel 2 or Corning dinnerware. The difference between them is this, that the Vitrel 2 dinnerware, which is on your right, this is a set that I have been using for over 32 years. The entire set is still in use. It has not chipped, it has not broken. I can take it from the refrigerator to the microwave oven. This is a dinnerware. And the one on your left, well, I'll come to it what is made of. That will crack if I try to take it from refrigerator to just a microwave oven. The one on your left is made from clay, ball clay. I would urge that you look up in the on your Google ball clay and find out what it is. Kaolin, again I urge you to look up what kaolin is. Quartz and feldspar. Percentages are rough. So first what was done for making this Chinaware, which will chip easily, looks good but it will chip easily. It is not thermal shock resistant, that it won't go from the refrigerator to the microwave oven. It has to be warm to room temperature, and in the microwave oven it will crack up. It was made by mixing this ball clay, kaolin, quartz and feldspar, and then shaping it into the form of plate, then applying the glaze on top of it, and we get this Chinaware. As I said, this is not thermal shock resistant, this is not microwave proof, this is not chip resistant, this is not scratch resistant. Let us take the next one, the one I showed. This is a dinnerware I've been using for over 32 years. No chipping. It is thermal shock resistant. It can be used in microwave oven. It can be used in harsh environment of dishwasher. This one, I have given a link below. Please look up this link. The reason is, it is an entire video demonstration of how these plates are made. This Corel dinnerware is basically a three-layered glass. The inner core is translucent glass. Or even opaque glass. The outer core is transparent. In fact, the whole technology of this Corel dinnerware is this, that you should look up the video to have a full understanding of the process. This is the mold on which the soft glass sheet is placed from the top. There are two ways. Either from the top a hammer comes in so that this glass piece now takes the shape of the mold, or air is sucked out and the soft glass piece assumes the surface of the mold. This comes here. You have to understand that right from the time the glass is melted to mold to heat treatment furnace, cooling, this takes place in only 15 minutes. The strength of this dinnerware is simply due to the fact that you have an inner core and, as I have said earlier, and a thin outer core. It is during this cooling process, because the surface gets cooled very fast, what happens is huge compressive stress is generated. During this cooling process, huge compressive stress is generated, and as a result, this becomes shatterproof, very hard surface, and hence much more long lasting. Of course, the property that it is the property that it is can be microwaved, can withstand thermal shock, these two are of course due to the constituents in the glass. This is in the Corel dinnerware. This is simply because of the constituents in the glass, because the process is so constant, thickness is uniform, heat transfer is uniform, that makes this particular glass, the Corel dinnerware, so thermally stable. Whereas in the previous one, this has been made by mixing the clay with the feldspar, kaolin, quartz, shaping it into the form of these plates, firing it for a long time, and here there is no melting. In this particular chinaware or in any other dinnerware, it is sintering. That is, the ball clay, kaolin, quartz and feldspar, they decompose and the grains join. Let me explain it a little further. Feldspar, to keep things very simple here, will have materials like sodium oxide, potassium oxide, calcium oxide, magnesium oxide, silica. Depending on where you are, the relative amounts will vary. These melting point is low. Depending on the place, it can melt at temperatures as low as 800 degrees centigrade. Now let us keep things simple, very simple. Let me take that I have got quartz, I have got clay which includes kaolin also plus feldspar. We have taken these materials, crushed, I will define what is crushed later during the course, and then mixed in whatever ratio you want. So essentially now we have a powder which has got a physically mixed composition of quartz, clay which includes kaolin and feldspar. Now this material you have seen potter's wheel. So let us, for brevity's sake, simplicity's sake, assume that we have taken this material on a potter's wheel, have shaped it into the form of a glass, let us say, or a cup, or even the earthenware from which you drink your tea at railway station, because they all come from the same roughly same compositions, and then they are fired. The firing temperature will vary. Say the cups, the earthenware cups from which you drink your chai at tea stations, some are very thin, they have got a lot of kaolin, some are thick which has got grainy soils. But let me not dwell on that right now, but let us say somewhere we are firing it at 1200 degrees centigrade at most. Now if I take the material and look at it under a microscope, what will I see first? What I shall see is there will be sand grains, there will be clay particles, lot of clay particles. Let me mark the clay by X. There will be lot of sand grains, let me mark it by S. There will be some feldspar, there will be feldspar also. This is how the thing would look under a microscope. When it is heated to 800 degrees centigrade, what happens is that feldspar melts. And we land up with, let me say these are sand. Now because it is getting to be more complex, let me draw sand particles in blue. This is sand, 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 sand. All of these are sand particles. I will have clay, remember. So I will have clay. The green ones are clay. Let me do that also. So this is clay, 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 clay. And I said feldspar is melted. So now all this area is filled with molten feldspar. As this material is heated past, let us say here I said 800 degrees centigrade or so, as it is heated past 1100 degrees centigrade, you will see later that the kaolin decomposes to give you silica and the rest of the materials. But let me focus on one thing, is sand is pure silica. Clay, which includes kaolin, is a mixture of silica, alumina. So these are called basically aluminosilicates. That's what the word keramos came from. What happens is this: now at 1100 degrees centigrade, if I keep it here, yeah, if I keep it here, what happens? I have got the feldspar now coating the sand and the clay particles. The feldspar at this stage reacts with both sand plus clay which has decomposed. And this microstructure then changes to something like this. Sand is blue, fine. So I'll have sand grains, sand grains, sand grains, sand grains. And there's a whole of a lot of liquid over here. This is all liquid. This is all liquid over here, which are surrounding the sand grains. This liquid is very rich in sodium oxide, whatever is there, potassium oxide, calcium oxide, very rich in alumina, very rich also in silica, all of which have been derived from feldspar melt reacting with the clay. As the temperature increases more, with more sintering, what happens is something like this. This liquid, as the feldspar has dissolved totally, it has reacted with the kaolin contents and the clay contents, and the liquid has become richer and richer in alumina and silica. It becomes very saturated with a particular product called mullite. I could have given you the composition of the mullite right now, but mullite is a fascinating thing. So I would urge you to Google mullite and find out what it is. So now, at this particular stage, where this liquid has become supersaturated with a lot of alumina silica, what happens is this, that this particular mullite, because the liquid has become supersaturated, separates out, and mullite needles start growing out. They start precipitating out, and they need the mullite that is coming out, which is also from the layer of sand which has dissolved over here, they sort of interlock as their hands, as my fingers have. The more the interlock, the more the strength. So when you go to the market and look for a cup may cost you 2 rupees, or if you look at the top level cup which is made from this kaolin process, it can put me back by 400 rupees, but both are cups. The thing is, in the cup that I bought for 2 rupees, this firing has not been taken to conclusion. Whereas in the 400 rupee cup, there is extensive mullite growth, extensive bonding, and the strength of the material has increased hugely. This is of course done by having purer and purer clay. The 400 rupee cup would be using what we call China clay, a very, very white clay, almost like kaolin. It would be using that. It would be very free of impurities, and as a result, the 400 rupee cup is much stronger. It is also thinner, whereas the 2 rupee cup is definitely thick. In this ceramic fabrication and processing course, we will look at such events as to how to control sintering, microstructure, so that we can get very good products. Now, before I move over, I want to emphasize this particular material which you are seeing, a Chinaware, is a sintered product, whereas this Corel dinnerware is a molten ceramized product. I urge you to look at the video to have a real appreciation of how a ceramic, of how this Corel dinnerware is made. As I said, I have it for over 32 years, and you can see the patterns are still there, nothing has gone. I say Corel because I have it, but yes, there are at least 4 other companies in the world who make identical wares as good as Corel. Many of you have heard of refractory bricks. The one on your left which is shown is a 99% alumina refractory brick which can withstand temperatures up to 1950, 2000 degrees centigrade. It can be used in the hot phase, or it is used definitely in the hot phase of any steel melting furnace. It looks very similar to another one which is now coming up on your right. This is also an alumina based refractory, only the one on your right has got around 40% alumina. The one on your right which has 40 to 50% alumina weighs a third of the refractory to your left. So, and the refractory to your left, which I said can be used in the hot phase, the refractory to your right is very porous and it is used as an insulating refractory at the back of the blast furnaces. So, it is the same refractory. This is another joy of ceramic processing. It is the same material, either it can be made very dense or it can be made very porous. Let me give you an example of use of porous ceramics. All of you use gas burners at home. The burner head is made up of metal this size. It has got 1 millimeter hole. Now, if you look up this company's Faber, this is just one company, this is no endorsement of any company. Faber gas cooking range. This will have 4 burners. 3 of them are conventional And the fourth one is a porous ceramic burner. Pore sizes in the burner are of the order of 10 micrometers. And as I said, these are conventional burners with holes, and these holes measure 10 to the power of minus 3 meters. Remember, 10 to the minus 10 micrometers means 10 to the power of minus 10 meters. So the porous burner, the pore size is that fine, while in the conventional ones, the pore size is 10 to the power of minus 3 meter or 1 millimeter. Burning efficiency, that is, how much of the gas is burnt, is only 15%. Here it is 85%. This porous ceramic burner is an offshoot of industry, because in, say, glass melting furnaces, what they do is, schematically say showing, they have huge tanks, 100 feet, 50 feet high. This has all the sand and other materials, and they used to have burners blowing from the sides. It would, the length would be anywhere up to 100 feet. So they had lots of burners which were needed to melt this material. Problem came in is, one, these burners low efficiency and emit nitrous oxide, carbon monoxide, both of which are, well, environmental pollutants. So today, the glass industry are gradually shifting to tanks which use porous gas burners. Right in the sides. From the gas burner, no flame comes out. In your house, in the gas burner, there is always flame coming out. But in these porous ceramic burners, there is just no flame, because of the very fine pores here, they burn right over here. And once these porous burners are embedded in the melt, they just burn, and heat transfer is very high. So the burning efficiency increases, heat transfer rate increases, and that is one of the biggest uses of porous ceramics that has come about while we are looking at environmental issues. More on these porous ceramics I will cover during my course. So let us look at roughly now the scope of this particular course. Now you know ceramics have been used as refractory materials, as tiles. In older refrigerators, glass fibers have been used as insulants. You see, many high rises are now coming up, basically steel and glass structures. and those glasses have a coating. What are those coatings for? Those coatings are to reduce heat inflow. That is, right in Delhi, when the temperature is hovering at 46, those coated glasses prevent the heat from coming into the room, and they also reduced light transmission, so that lighting inside can be controlled. I'll talk of this much more later when I take up on coated glasses. Apparently, when you are on the road, you do not see anything inside. But trust me, those persons who are sitting inside have a clear view of what is going on outside. So these are a sort of one-way glasses also. Windows. With these high rises coming up, these windows need to be earthquake proof also. You have seen many accidents happen on the road. You have seen how the glass windshield in the front breaks. If it doesn't break, yes, it breaks, but then it doesn't throw shards of glass here, right, left, and center. Why? Because the front windshield has a laminar construction. It is a two glasses sandwiched with a polymer sandwich in between. So even if the glass breaks, this polymer prevents the glasses from flying off. It is true that both the glasses are tempered, means both the sheets are heat toughened, but for added passenger safety, this lamination is used. Now, in all these high rises which you see, to make them earthquake proof, such laminated glasses are being used. But then the problem is, one really does not know how they will behave when an earthquake is on, because it will be repeated cycling. So efforts are now on today to have glasses which will be earthquake resistant by itself. I can give you a hint now as to how it is being done or is planned. All of you, I guess, must know about the destruction of the Twin Towers, 9/11, and the plan to construct a new building which would be proof in all ways that humans can design, and it was supposed to be made of steel and glass. Well, suffice to say that $10 million has been spent on a pilot project as to how to make earthquake a glass which would withstand the impact of a plane coming in, as it did, that is impact proof also, and the concept has failed. So we are looking at newer and newer ways as to how to make these glasses, and the question is open. I have talked of dinnerware. Now let me talk of what I have written, oven top cookware and oven top cookware. This is a glass vessel Looks beautiful. There are patterns on it. But my problem is, if I try to pour or heat or put it in an oven, this will crack. This one, I can heat on a gas flame, cook in it, and then immediately put it in cold water. It won't crack. I try to heat this in a microwave oven, this will crack. This one will not crack. This is really called an oven top cookware, in which I can cook even on top of a gas stove and then place it on a cold plate or even water. So there is a substantial difference between this and this. The difference is that the oven top one this is a glass ceramic. Most of you have been told that a ceramic is either crystalline or non-crystalline. Glasses don't crystallize. But in this oven top cookware, which is a glass ceramic, if I use block diagram, I would melt the glass, shape it, and heat it. Under controlled temperature. Once it has been shaped, the temperature is obviously nowhere near the melting temperature, because the melting, this may occur at 1300 or even 1350 degrees centigrade. By the time I have shaped it, the temperature here has fallen to 700 degrees centigrade. So this shape, when in mold, is anywhere between 500 degrees centigrade to 700 degrees centigrade. It's a rigid body. Of course, it will deform if you apply pressure. This is then heated under controlled conditions. Somewhere around 550 degrees centigrade, and this is where something happens. Right at this stage, if I take a section of the glass and look at it under a high power microscope, all I will see is a transparent material. But as it is heated at 550, with time, very fine crystals start separating out. Very fine crystals start separating out. The longer the time you give, you will have more particles separating out. Here is this temperature, this time has to be calibrated, because if these particles become too thick, this glass will not be transparent anymore. So we have to ensure that these particles are fine enough than the scattering diameter. Wavelength of light is anywhere from 360 nanometers to 800 nanometers. And hence, you know, scattering will occur at wavelengths sizes greater than lambda by 4. So here we need to maintain particle sizes below, let's say, 70 nanometers. Doing this gives us a lot of options. In this particular transparent glass, what I have is very ultrafine particles. They allow very high thermal conductivity. They prevent crack propagation, because cracks, as you know from your basic engineering courses, will stop when they come to a particle. And as a result, this particular glass, which is a glass ceramic, can withstand high thermal cyclings, which is thermal shock. This can be microwaved, and this is much more stronger than this particular glass. If I look at the microstructure of these two, and if I take a small broken piece and look at these two under a microscope, to repeat it, I will see only a glass over here. But over here, what I will see is a glassy matrix with very ultrafine particles distributed right through, of sizes less than lambda by 4, which gives it exceptional strength, exceptional thermal cycling property, and they don't break. This glass ceramic is at the heart of generating strengthened glass. Sure, tempered glass as seen in automobiles are strong, but when we are talking of earthquake proof resistant glasses, we need to ensure glasses which won't crack. And hence, one of the techniques that is being used to make earthquake resistant glasses is the glass ceramic way. Unfortunately, $10 million have gone to waste, and we are back to the drawing board. But that has left us with a lot of knowledge we have gained, and maybe will come through. So essentially the glass ceramics form a very high component of high strength glasses. I will again, before I finish off, I would like to raise one more issue. Is, let's say this new building comes up, it is all steel and glass as it has been planned, and suppose we can make the earthquake resistant glass. How do you clean the outer surface? You cannot send someone 200 stairs up to clean the glasses regularly. So now the third part, one, I said those glasses will be earthquake proof. Secondly, they will be thermally insulating, they won't allow heat much. Third, they will have to be self cleaning. Now if you Google the term self cleaning glasses, you look at for images in Google, in Google, you will see that the glasses like lotus leaves never aqua dust. Nobody has ever seen lotus leaf covered with dust because the water washes it away. So, all these glasses are self cleaning, earthquake resistant, and also control heat and light. In summary, up to now I would say, even though ceramics is over 26,000 years old, the first glass vessels were made around 4,000 years ago. We are still evolving. Thank you.